Hello and welcome. My name is Vineet Kumar Mishra and I am presenting this Assignment 1 of Heat Transfer to Dr. Sasikant Yadav, Assistant Professor, Department of Chemical Engineering, NIT Jalandhar. So let's start. The topic of the assignment is dimensional analysis. Before we go into nitty-gritties of dimensional analysis, let's see this famous quote. Take care of your units and they will take care of you. I'm repeating again. The quote is, take care of your units and they will take care of you. Now, what does this mean? Like at some time in every engineer's life comes the exasperating sensation of frustration in problem solving. Somehow the answers or the calculations do not come out as expected, and often this outcome arises because of errors in handling of units. So the use of units along with numbers in our calculations requires more attention than we probably have been giving to our computations in past. In addition to that, checking the consistency of units in our equations will prove to be a valuable tool, and that will reduce the number of errors we commit when performing engineering calculations. So it is very important that we should be very careful about our units in problem solving, in computations, etc. So this is a very good quote, like take care of your units and they will take care of you. Alright. Now, what are the objectives of this video assignment? First of all, I'll be discussing introduction to dimensions and units. Why dimensions and units? Because in the dimensional analysis, our main focus, our main concern is on the dimensions only. So we'll be discussing dimensions and units, their introduction, type of dimensions, and all other things. Thereafter, I'll be discussing dimensional analysis, what actually the dimensional analysis is, and how we can apply this method, how we can apply that concept, and what are the different methods of dimensional analysis. We'll also see an example, and thereafter and different applications of dimensional analysis also. Then after we'll see use of dimensional analysis in real life, where we can use the principles, the concepts learned in the dimensional analysis, where we can apply all other things we'll see. Thereafter, dimensional homogeneity. In dimensional analysis we apply the principle of dimensional homogeneity also, so we'll see that also in upcoming slides. And different methods of dimensional analysis also, like there are two methods we'll see in detail. Different methods, their advantages, their disadvantages, and where we can apply which method, all other things we'll see in this. And last but not least, we'll see an example problem to explain the concepts. With the example, our concepts will be much more clear. So we'll see an example problem at the end. Alright, so let's start. First of all, dimensions and units. The question is why we need to study dimensions and units. Because engineers and scientists have to be able to communicate not only with words but also by carefully defined numerical descriptions. So that's why we have to study dimensions and units. And what happened, like in dimensional analysis we are only concerned with the nature of dimension, that is its quality, not its quantity. We are concerned about the quality of the dimension, not about its quantity. What does this mean? Like in dimensional analysis problem, like we always try to reduce the number of variables in any of the physical problem. So So that is written here that we are concerned about quality, not its quantity. We always try to reduce number of variables, that is its quantity. So it is correctly written over here. In dimensional analysis, we are only concerned with the nature of the dimension, that is its quality, not its quantity. Now, what the dimensions are actually? So dimensions are the properties which can be measured. So any of the property that can be measured is called dimension. For example, we want to measure mass of any object. So mass is a dimension. We can measure mass in kilogram, we can measure mass in gram, we can measure in pound, and like we want to measure mass, so we can measure in kilogram, in pound, in gram, or any other unit. So we can measure mass, so mass is a dimension. Similarly, length, we can also measure length in meter, centimeter, inch, feet, whatever. So it is also a dimension. Similarly, time, or there may be other dimensions like temperature also, and many other. All right. Now, what are the units? Units are the standard elements. Units are the standard elements we use to quantify these dimensions. To quantify the dimensions, we use units. Suppose we want to quantify the mass, so what we will use? We will use kilogram, we can use pound, we can use gram. I have written kilogram here in MKs. Similarly, for length, we can use meter, centimeter, kilometer, feet, inch, whatever. So in MKs, it is meter. Similarly, for time, it is second. If we take temperature, it's Kelvin or degree centigrade, depending upon type of system which we will be using in our problems. Here I have written all the in MK system. And dimensions are actually of two types. One is the fundamental dimension and another one is the derived dimension. Here we will see fundamental dimensions, and in upcoming slides, in the next slide, I will be discussing about derived or secondary dimensions. So here the fundamental dimensions are like mass, its unit is kilogram in MKs of course, and its dimension is m. Similarly, for length, its unit is meter m, and its dimension is L, and time, the unit is S, and dimension is T. If we take temperature, so unit will be like Kelvin, and dimension we can take theta or T sometimes also. So this is about dimensions and units and fundamental dimensions. Alright, in the next slide we will see secondary or derived dimensions. So now, secondary or derived dimensions. What are the secondary or derived dimensions? So as it is written, secondary dimensions are those quantities which possess more than one fundamental dimensions. Means when fundamental dimensions are combined together, we get secondary dimensions or derived dimensions. It is also called derived dimension. For example, area, unit is meter square and dimension is L square. Now I'll show you how this is L square. Suppose, what is the formula of area? Area is the length into breadth. Okay, length we use meter L into L, so it is L square. Alright, and for other also I'll show you, just a minute. Suppose I take velocity. So what is the formula of velocity? B is equal to distance per time. Distance we measure in L and time in T, so it is LT minus 1, which is written here. Alright. Similarly, for acceleration is velocity per unit time, so LT minus 1 divided by T, so it will be LT minus 2. And for force, so the formula of force is F is equals to ma, where m is the mass and a is the acceleration. So the dimension of the force will be mass into acceleration, m into a. The dimension of mass is simply m, and that of acceleration is lt minus 2, so it will be mlt minus 2. Here I think there is a mistake. Here it should be mlt minus 2, mlt minus 2. Okay, it's a mistake. Similarly for density, what is the formula of density? Density is simply mass by volume. I'll show you. Density we write as rho. It is simply mass divided by volume. For mass m and for volume it is L cube, so it is simply m L minus 3. Okay, as it is written. So these are the secondary or derived dimensions. Means when we combine one or more two or more fundamental dimensions together, then we get secondary dimensions or derived dimensions: area, volume, velocity, acceleration, force, density, to name a few. All right. Now next, now we are here with dimensional analysis. What actually the dimensional analysis is? Dimensional analysis is a means of simplifying a physical problem. How we can simplify? By appealing to dimensional homogeneity. As I told earlier also, that we use the concept of dimensional homogeneity in dimensional analysis. So that is written here. Dimensional analysis is a means of simplifying a physical problem by appealing to dimensional homogeneity to reduce the number of relevant variables. Means with the help of dimensional homogeneity, we try to reduce number of variables in any physical problem. And it is a pure mathematical technique. One more point to note here is it is a pure mathematical technique to establish a relationship between physical quantities involved in a physical phenomena by considering their dimensions. Means we will consider their dimension and we will establish a relationship. Alright, so it is a pure mathematical technique. Now what I have said, what is the objective of dimensional analysis? The object of dimensional analysis is to reduce the number of parameters in a problem. What I have said, the object of dimensional analysis is to reduce the number of parameters in a problem. Why we want to reduce the number of parameters? For ease of calculation and experimental economy. Why? Because of ease of calculation and experimental economy. And it follows that the best analysis will produce the minimum number of non-dimensional groups. So as these groups have physical significance, the non-dimensionalizing technique must always produce the correct scaling groups. And it might also be expected that this method, the method of dimensional analysis, should be applicable to a wide range of problems. The method of dimensional analysis should be applicable to a wide range of problems. It should be applicable to a wide range of problems. Right. And in short, if we want to say that the technique must be concise, correct, and consistent. It must be concise, correct, and consistent. So the technique of dimensional analysis should be concise, correct, and consistent. So this is about dimensional analysis. Now we'll see what are the different applications of dimensional analysis. So here I have listed down some of the applications, like presenting and interpreting experimental data. Dimensional analysis, the concepts, the method of dimensional analysis is very useful in presenting and interpreting experimental data. and also in attacking problems not amenable to direct theoretical solutions, means the problems that cannot be directly solved theoretically. For that we can solve those problems with the help of dimensional analysis. Also in checking equation, like again with the dimensional homogeneity, we can check the equation whether an equation is valid or not. We can check with the help of dimensional analysis, dimensional homogeneity, and establishing the relative importance of particular physical phenomena. And last, physical modeling. So these are some of the applications of the dimensional analysis. Now I'll show a simple example to demonstrate these things. Suppose we have a smooth cylinder, a long smooth cylinder, okay, and we want to know that the drag force F per unit length on this cylinder will depend on what parameters. Like the drag force per unit length on this cylinder will be the function of F, will be the function of air speed u, density rho, diameter d, and viscosity, of course, mu, viscosity mu. Alright, so the drag force per unit length will depend on air speed u, density rho, diameter d, and viscosity mu. However, instead of having to draw hundreds of graphs portraying its variation with all combinations of these parameters, like suppose if we want to see the variation, then we have to plot different like f with u, f with rho on different graphs. So but dimensional analysis will help us that the problem can be reduced to a single dimensionless relationship. Now what is that relationship? This problem can be reduced to a single dimensionless relationship. Now what is that relationship? Just a minute. That relationship is simply like CD equals to function of RE. Alright. So the dimensional analysis tells us that the problem can be reduced to a single dimensionless relationship, that is CD is equals to function of RE. CD is the drag coefficient and RE is of course the Reynolds number. So we have seen in this instance dimensional analysis has reduced the number of relevant variables. Like earlier we had 5 variables, 1 dependent and 4 independent, but now here we only have 2 variables. So in this instance, dimensional analysis has reduced the number of relevant variables from 5 to 2, and also the experimental data to a single graph of CD against RE. Now if we want to plot, we want to see the variation, so we can get in a single graph CD versus RE. And before the dimensional analysis, if we had to see the variation, then there were 4 variables, so we have to plot 4 graphs, and so that that will be very complicated. So this is the significance of dimensional analysis and applications. Now what is the dimensional homogeneity? Dimensional homogeneity means the dimensions in each equation on both sides equal. In any of the equation the dimensions on the both sides are equal, then we say that equation is dimensionally homogeneous. So actually the dimensional homogeneity is the concept where the dimensions of variables on both sides of an equation are the same. If the units are the same, the dimensions of each term must be the same, and every valid equation must be dimensionally homogeneous. If equation is not dimensionally homogeneous, we say that the equation is not valid. Now, what do I mean when I say that equation should be dimensionally homogeneous? That means all additive terms on both sides of the equation must have same dimensions. all additive terms on both sides of the equation must have same dimensions. So here is an example: b is equal to square root 2gh, where v is the velocity. So we know that velocity is equals to distance by time, so it is simply lt minus 1. So on the LHS we are having dimension lt minus 1. Now we'll see on the right side here 2, g is the acceleration of course, so dimension is lt minus 2 into h is height, so it is l, so it will be l2 t power minus 2 and with square root it is 2, so we'll get lt minus 1. Alright, so we have seen that in the LHS part there were velocity like and its dimension is lt minus 1, and in the right hand side we get lt minus 1. That means the dimension of LHS is equal to dimension of RHS. So the equation b is equal to square root 2gh is dimensionally homogeneous. So if the equation is dimensionally homogeneous, that means it can be used in any of the system of units. Alright. Now, methods of dimensional analysis. The number of dimensional variables can be reduced into a smaller number of dimensionless parameters by several methods. And commonly used two types of methods are Rayleigh's method and Buckingham Pi method. So there are two methods for reducing number of variables in any physical problem, and these two methods are Rayleigh's method and Buckingham's Pi method. Now what are these methods and what are the procedure of these methods, what are the advantages, disadvantages, we'll see. So first is Rayleigh's method. The first method is the Rayleigh's method. This method was proposed by Lord Rayleigh in 1889. This method was proposed by Lord Rayleigh in 1889. In this method, a functional relationship is expressed in an exponential form which is dimensionally homogeneous. I am repeating again. In this method, a functional relationship is expressed in an exponential form which is dimensionally homogeneous. As it is written over here also, like functional relationship between variables is expressed in the form of exponential relation which must be dimensionally homogeneous. Like if y is a function of independent variables or x1, x2, x3 dot dot xn, like suppose y is any variable, dependent variable which depend on independent variables x1, x2, x3 and so on xn. So we can write y as a function of these independent variables, y is equals to function of x1, x2, xn. Now we can also write these variables in exponential form, y is equals to phi, where phi is a constant. Phi is a dimensionless constant, and we can write it in exponential form like x1 raised to a, x2 raised to b, x3 raised to c and so on xn raised to z. Alright. Now procedure of Rayleigh's method. First, write MLT form of the given data. First of all, we have to write MLT form, and then we have to write the same equation in exponential form. Thereafter, select suitable system of fundamental dimensions. After writing the equation in exponential form, we have to select the suitable system of fundamental dimensions, and then substitute dimensions of the physical quantities. We will substitute the dimension of each of the physical quantities, and thereafter we will apply simply the dimensional homogeneity, equate the power on both sides, all kind of things. Now, as I told you earlier, equate the powers and compute the values of the exponent, and then substitute the values of exponent, and after substitution we will simplify the expression and we will ideal up in 3 independent variables. It can also be used for 4. Okay, so now I'll take an example to demonstrate what I have discussed. Let's suppose a1 is any dependent variable, a1 is dependent variable, and a2, a3, a4 and an are independent variables. A1 is dependent variable, A2, A3, A4 and so on, An are independent variables in a phenomena. So the functional equation can be written as A1 as a function of A2, A3 and so on An. Alright. This equation we can also write it in exponential form, like using powers a, b, c. So we can write it as a1 is equals to k a2 power a. It is not clear. It's okay. A3 power b and so on an power n. We can write it in an exponential form where k is the dimensionless constant. Now after writing in exponential form, what we will do, the dimension of each of the quantities of like a1, a2, a3, a4, an are written, and the sum of the exponents of the functional quantities on both sides are equated. After this we will write the dimension of each of the term and the sum of the powers will be equated, and then we will get the solution like the values of a, b, c, etc. So after solution of the equation, the values of a, b, c and so on are found out, and these values are substituted in the main equation. Then these values will be substituted from the new main equation. After simplification yields dimensionless groups controlling the phenomena, and after the procedure we will get dimensionless number of groups. Alright. So, but what is the disadvantage of religious method? Disadvantage of this method is like when a large number of parameters are involved, this method becomes complicated. Like for 2, 3, 4 variables, this method is, we can use this method. The computation will not be that much difficult. But when a large number of parameters are involved, then this method becomes complicated. And also, religious method doesn't provide any information regarding number of dimensionless groups to be obtained as a result of dimensional analysis. And one more disadvantage of this method is like when we do dimensional analysis by religious method, it will not give any kind of information regarding how many number of dimensionless groups will be getting after the analysis. So this is again a major disadvantage of this method, and when any disadvantage came, then we will shift to next method. So the next method or the second method of dimensional analysis is Buckingham's pi method. So it is a more generalized method of dimensional analysis. It was developed by E. Buckingham and others, and it is most popular now. This arranges variables into a lesser number of dimensionless groups of variables, and because Buckingham used pi to represent the product of variables in each groups, we call this method Buckingham's pi method, pi theorem. So according to this theorem, if there are n dimensional variables, according to this theorem, if there are n dimensional variables, like in any of the physical problem, if there are n dimensional variables in a dimensionally homogeneous equation described by m fundamental dimensions, and we can describe in m fundamental dimensions, then they may be grouped in n minus m dimensionless groups. Okay, Buckingham referred to these dimensionless groups as pi groups, so we call this as Buckingham's pi theorem. Now what is the advantage of using Buckingham's pi theorem, Buckingham's pi method is, the advantage of this theorem is that one can predict number of dimensionless groups are to be expressed. Like in the religious method, we were not able to find the number of variables, number of dimensionless groups after the dimensional analysis, or we were not able to predict that. But here In this method, in Buckingham's pi theorem, we can predict the number of dimensionless groups are to be expressed. So this is the advantage of using Buckingham's pi method. Okay. So if n total number of variables in a dimensionally homogeneous equation containing m fundamental dimensions, then they may be grouped in n minus m pi terms, as I told earlier, and then they can be expressed as function of x1, x2, xn equals to 0. Then the functional relationship will be written phi 1 pi 2 dot dot pi n minus m equals to 0, as there will be n minus m terms. And the final equation obtained is in the form of, like, pi 1 will be the function of other pi terms like pi 2, pi 3 and so on, pi n minus m. This method is mainly suitable for the variables where n is greater than or equal to 4. But this will not be applicable if n minus m is equal to 0. Means if the number of dimensional variables and number of fundamental dimensions are the same, then we cannot use Buckingham's pi theorem. Why? Because a number of pi terms is n minus m. So when n minus m is 0, that means there will be no pi terms. So we cannot use this method for when n minus m is equals to 0. Alright. Now we will see an example problem to demonstrate whatsoever we have discussed till now. We'll do a dimensional analysis for H. What is the H? H is simply the heat transfer coefficient. So from different experiments, it has been seen that H, that is heat transfer coefficient, in forced convection depends on rho, which is density, V volume, L characteristic length, mu viscosity, Cp which is heat capacity, and K which is thermal conductivity. So from different experiments, it has been seen that H in forced convection depends on rho, V, L, mu, Cp and K. Hence we can write it as function of H is equals to function of rho, V, L, U, mu, Cp and K. Alright. Or we can also express it in exponential form. So in the exponential form, it will be like H is equals to A is a dimensionless constant, rho raised to A, V raised to V, L raised to C, mu raised to D, Cp raised to E and K raised to F, where A, small a, V, C, D, E, F, these are dimensionless constants. Right. Now after writing the exponential form, we will write the dimension of each of the terms. So for H, the unit is watt per meter square Kelvin. It is heat transfer coefficient and its dimension is mt minus 1 t minus 3. Here T is for the temperature, capital T is for the temperature, small t for the second or time. So for the heat transfer coefficient for the H, it is mt minus 1 t minus 3. Next rho, which is density. We know density is mass by volume, kilogram per meter cube. So its dimension is ml minus 3. Mass divided by volume, it is ml minus 3. Next is the velocity. Velocity is what? Distance per unit time. Distance is L, time is t, so it is simply Lt minus 1. L is the characteristic length and its unit is meter and dimension is L. Similarly mu, which is viscosity, its unit is kilogram per meter second, and according to that dimension will be ml minus 1 t minus 1. Cp is the specific heat or heat capacity and its unit is joule per Kelvin kilogram or meter square per second square Kelvin. So its dimension will be L square T minus 1 small t minus 2. And for thermal conductivity K also, its unit is watt per meter Kelvin, and dimension will be mLT minus 1 small t minus 3. So basically, after writing the equation in exponential form, we have written the dimension of each of the terms. For H, heat transfer coefficient, it is mt minus 1 t minus 3. For rho, it is ml minus 3. For V, it is lt minus 1. For small l, it is L. For mu, it is ml minus 1 t minus 1. For Cp, heat capacity, it is L2 t minus 1 small t minus 2. And for K, which is thermal conductivity, basically thermal conductivity is the ability of any material to conduct the heat is called thermal conductivity. So it is expressed watt per meter Kelvin. So its dimension is mlt minus 1 small t minus 3. All right. Now we will substitute these dimensions in the exponential equation. So we'll see in the next slide. Now here I have substituted all the values, like first mt minus 1 t minus 3, then all the values like ml minus 3 raised to a, lt minus 1 raised to v, l raised to c, ml minus 1 t minus 1 raised to d, l2 t minus 1 small t minus 2 raised to e, ml t minus 1 small t minus 3 raised to f. Now we'll equate all the powers. Like suppose in the LHS the power of m is simply 1. In the right side, first we get a, here no, here d, and here f. So as it is written here, 1 is equals to a plus t plus f, first equation. Now for the power of L, LHS we have no powers of L, so it is 0. In the RHS we are having like minus 3a, and then it is V, then it should be minus 3, I think that is a mistake, then D, then 2e, and then F. So this is about L. Next for the temperature, in the LHS minus 1, the RHS minus E minus F. So third equation is of the powers of the temperature, and the fourth one is about time. So in the LHS we are having like minus 3, in the RHS here no powers, here minus B, then minus D, then minus 2e, and minus 3. So this is like we have equated the powers of each of the terms for m, for L, for T, for small t. All the powers we have equated the powers of each of the terms. So now from this we can solve these equations. Now let us obtain values of all constant in terms of only two constants, say a and d. Now we will find the value of each of the constant in terms of only two constants, like a and d we have taken. So the equation will be something like this: h is equals to a is the dimensionless constant, of course, as I have discussed earlier also. A, rho raised to a, v raised to a minus 1, mu raised to e minus a, cp raised to e, and k raised to 1 minus e. So we have written all the variables in terms of two variables only, a and e. Now we can group them further. H is equals to a rho v L by mu raised to a, mu cp by k raised to e, and k by L. We can also like this, or we can also write like HL by k, we have taken this term to this side, or a rho v L by mu raised to a, rho cp by k raised to e. So what we did, we we express all the variables in terms of only two variables, a and e, and then we have arranged, and then at last, after arrangement, we get this equation: HL by k equals to a rho VL divided by mu raised to a. It is in power, it is also in the power, mu Cp by k raised to e. So now we can write it as, Nu is equals to a Re raised to a Pr raised to e. Now what is this Nu, Re, Pr? These are the dimensionless numbers. These are the dimensionless numbers. We will see one by one what are these numbers. So Nu is the Nusselt number. Nu is the Nusselt number. Nu is the Nusselt number. And what is this? And the Nusselt number is defined, and it is the ratio of convective to conductive heat transfer. What is the Nusselt number? Nu is the convective to conductive. Nusselt number is the ratio of conductive heat transfer coefficient to convective heat transfer coefficient to conductive heat transfer coefficient. So we can write like convective heat transfer coefficient, we can write it as H, and conductive heat transfer coefficient we can write as K by L, where H is the heat transfer coefficient, of course, and K is the thermal conductivity, L is the characteristic length. So this is about Nusselt number. Nu is the Nusselt number. It is the ratio of convective to conductive heat transfer coefficient, and it can be written like HL by K. We have substituted for this. L will go up. So this is HL by K equals to Nu. H is the heat transfer coefficient, K is the thermal conductivity, L is the characteristic length. Now what is the PR? I'll discuss just a minute. We have to erase this. Sorry. Yeah. So what is the PR? PR is the Prandtl number. PR is the Prandtl number. So what is the Prandtl number? It is also a dimensionless number, of course, and it is named after German physicist Ludwig Prandtl. The Prandtl number is named after the German physicist Ludwig Prandtl. This is named after the German physicist Ludwig Prandtl. And what is the definition of Prandtl number? Prandtl number is simply defined as the ratio of momentum diffusivity to thermal diffusivity. Again, Prandtl number is defined as, like, PR is defined as momentum diffusivity divided by thermal diffusivity. Okay, so momentum diffusivity we can write as like nu divided by alpha. It is nu. We can write is that nu is the it's the kinematic viscosity. Of course, like momentum diffusivity we can write in kinematic viscosity, in terms of kinematic viscosity. So 1 second. So we can write PR as nu by alpha. Nu is the kinematic viscosity, which is of course the dynamic viscosity divided by density rho, and alpha will be like K by alpha is K. Sorry, I'll write here. Alpha is K divided by Cp into rho. So when we combine these two terms, we will get PR is equals to Cp mu divided by K, which we have substituted earlier, like mu Cp by K is equals to Pr. So Pr is the Prandtl number and it is Cp mu by K, momentum diffusivity divided by thermal diffusivity. Cp is the heat capacity, mu is the dynamic viscosity, and K is of course the thermal conductivity. Alright, now one more term is here, this is Re. What is Re? Just a minute. So far I have discussed about Nu, which is Nusselt number, and Pr, which is Prandtl number. One more term is here. A is the dimensionless constant, so I will not be discussing that. Re. Re is the Reynolds number. Reynolds number. R is the Reynolds number. And if we talk about definition of the Reynolds number, so it is simply the ratio of inertial forces to viscous forces. Reynolds number is simply the ratio of inertial forces to viscous forces. And actually the Reynolds number help us predict flow pattern in different fluid flow situations. Like if the Reynolds number is low, like at low Reynolds number, flow tend to be dominated by laminar. Laminar means like parallel sheet like flow. And at high Reynolds number, flow tend to be turbulent. So basically Reynolds number help us to predict the flow pattern in different flow situations, different fluid flow situations. So definition I have earlier talked, like Reynolds number is ratio of the inertial forces to viscous forces. Okay, so I think I have discussed all the terms. So we have reduced the number of variables from, like, how many variables were there? H, rho, V, mu, Cp, K. 1, 2, 3, 4, 5, 6. Earlier there were 6 variables. Now we have grouped it into 3 dimensionless variables: Nu, Nusselt number; Re, Reynolds number; and Pr, which is the Prandtl number. So this is the advantage of dimensional analysis. Now the calculation will be easy. Calculation will be very easy, and this will help us like in prototype designing, in physical modeling, in many other situations also. So dimensional analysis is very great tool. Another method of dimensional analysis, Buckingham Pi method, which I have discussed earlier also. So that method is much more better than this which I have used, Rayleigh's method. So this is all about dimensional analysis. So, and that brings us to the end. Thank you. And thank you so much for your interest and attention. Thank you.